And this is what we expect. We will keep hearing sounds from the universe, similar to those which we have detected. So let's go back 100 years, because I'm telling you about gravitational waves, but I really need to introduce them and explain what they are. So 100 years, because in 2016, Einstein postulated the existence of gravitational waves. You guys may have heard about 100 years of general relativity. In, did I say 2016? 1916, he postulated. So in 1915, he came up with the GR theory, and it had a direct consequence, which he realized basically right away, because in a year he put out a paper, and in another 2 years he put out another paper which actually was the correct description of gravitational waves. So that's the history. Einstein never believed that we are gonna be coming here and talking about gravitational wave detections, because he said this effect is so minor that there will be never an instrument which can actually make this observation. He didn't believe this could be done, what was done by the LIGO collaboration. So gravitational waves, well, they are just waves, first of all. You understand the concept of a wave. You drop a stone in a pond, and you're going to see waves propagating on the surface of the water. So in that sense, the water would be your medium for the propagation of the waves. So what would be the medium for the propagation of gravitational waves? You may have heard that gravitational waves are ripples on the space-time. So let's discuss what space-time is, fabric of space-time. So we have the Earth there and the Moon, and this mesh here would be what we would call space-time. You may have seen this image before, or something similar. So Earth has a very heavy, Moon is a bit less heavy, and it bends space-time. And you see that all these spheres have a different shape when we get closer to the Earth. It's bent and it's no longer symmetric, right? So, of course, there is a bit difficult to understand what really space-time is from this two-dimensional space description. So right now here we have only two-dimensional space, okay? And we use the third dimension to introduce and show the bending. I still could not find very good description, but this would be another one that you sort of could imagine that bending happens in three-dimensional space. So I just want to make sure that bending, that well is not real in terms of spatial dimension. The well has to do with the very high mass of that object which bends the space around it. And higher the mass and more compact the object is, then this bending will be even more. Okay? It's very difficult to visualize in 3 dimensions. This is why you guys keep saying, and I will keep showing the 2-dimensional description. So I said we need very heavy objects. Let's say, what are the heavy objects? Is our sun enough? Well, it's heavy, but it's not that compact. Let's push and squeeze our sun, or 1.5 times the mass of our sun, into the size of Manhattan, and we get something which we call a neutron star. But there are even more compact and heavy objects which are called black holes. So, of course, they bend space-time as well. And this is just a description. Similarly, let's say a very heavy black hole. You don't even see the bottom of the well. Again, this is just 2-dimensional. And I showed this figure for you guys as well, because this is made at the World Science Festival. I'm there every May, and we entertain children and tell them about space-time. And they can have this very fun game where we put a heavy object at the center of this we call space-time spandex demonstration. And they can play with the little marbles and enjoy and learn a little bit about black holes. But look at these situations. In these cases, the space-time is something not really stormy, it's calm, nothing is moving. So we have a heavy object, yes, there is a black hole at the center, space-time is bent, but this is calm, okay? We don't have a wave yet, so where do those waves come by? Well, we need to have not only one object, but two objects. And they have to do a given dance. You know, in physics terms, we say we need to have what we call radiation, not that, but that's not enough, but that's too much terminology. So a good example for creating gravitational waves would be two heavy objects doing this, moving around each other, getting closer and closer, closer and closer, and at the end they merge. And then they create gravitational waves. So that would be a storming space-time, right? And these gravitational waves actually propagate further and further, and they may reach us, okay? Of course, we really need those heavy objects. So I'm doing this right now, and I am actually creating gravitational waves. It's hard to believe, but I'm doing that. Okay, you can do that and create gravitational waves yourself, and we can even calculate how much that would be. It's totally non-observable. This would be really at the level of, yeah, I don't think we will ever observe it. But if those two objects have incredibly compact, and therefore they bend space-time quite a bit, then that gravitational wave may be observable. So let's see, this was in 2 dimensions, and this is the way it would look like 3 dimensions. So I showed you just a figure. Actually, it was a real simulation. This is also a part of a simulation from a 3-dimensional simulation. And this can be done, and science is there that this is done pretty regularly. The last 10 years were really amazing in this field of which we call numerical relativity. I will tell you a little bit more about that because you will ask me how do we know what we have seen are 2 black holes. And numerical relativity has to do something with that. So let's go back to that we will need 2 neutron stars or 2 black holes doing this dance. And then we can measure something at the order